In the introduction of coordinate representation relative to a basis, we mentioned that it has applications in robotics and humanoid. In designing those, it's important to identify the position and orientation. So the coordinate relevant to a different basis is a hot topic in also machine learning and deep learning. The definition is, suppose you have an ordered basis like B, V1, V2, Vn. For a vector space like V, and X is a vector in vector space of V. You can write X as a linear combination of these vectors in the basis. Of course, you end up with some coefficients C1, C2, C3, Cn. The scalars C1, C2, C3, Cn are the coordinates of X relative to the basis B. The coordinate matrix or coordinate vector of X relative to B is the column matrix in N space whose components are coordinates of X. We represent it this way. We take the basis, we use open, close square bracket, we put X there, and then the index is B. And on the right-hand side, you have a nice column vector. For example, suppose you have this vector X, -2, 1, and 3, and you want to find the coordinate matrix of this vector relative to the standard basis. Remember the standard basis, E1, 1, 0, 0, E2, 0, 1, 0, and E3, 0, 0, and 1. Well, as you know, -2 times 1, 0, 0, plus 1 times 0, 1, 0, plus 3 times 0, 0, 1, basically form this vector. So the coordinate matrix of X relative to the standard basis is this column vector, -2, 1, and 3. The components of X are the same as its coordinates relative to the standard basis. Now, suppose you have a vector like X in the plane. The coordinate matrix of X relative to non-standard ordered bases B, V1, and V2, which is defined as 1, 0, and 1 and 2, is as follows. You have 3 and 2. It means that that vector X can be written as a linear combination of these two vectors with scalars 3 and 2, C1 and C2. Now the question says find the coordinate matrix of X relative to the standard basis. The previous one was non-standard. As you can see, you have 1, 0, but this guy is not 0 and 1. This is 1 and 2. Now the question says find the coordinate matrix of X relative to the standard basis, which is, we all know, 1, 0, and 0, 1. Let us start. The coordinate matrix of X relative to B is denoted by the square bracket X with index B, which is given to us as 3 and 2. What's the meaning of that? It means that X can be written as 3V1 plus 2V2, or 3 times 1 and 0 plus 2 times 1 and 2. If you simplify this, you can construct your vector X, 5 and 4. You can easily write this in terms of 1 and 0, 0 and 1. It is 5 times 1 and 0 plus 4 times 0 and 1. So you can simply write the coordinate matrix of X relative to B prime as 5 and 4. You can visualize this as well. The visualization for non-standard basis is as follows. So V1, which is 1 and 0, is denoted this way, and V2, which is 1 and 2, is denoted this way. 3 times V1 plus 2 times V2, if you add these two vectors together, give you this vector X, 3 and 2. However, if we just write it in nicer format, a nice plane with x-axis and y-axis, U1, 1 and 0, U2, 0 and 1, 5 times U1 plus 4 times U2 gives you this 5 and 4, which is your vector that you saw in calculus, and you work with these a lot. So again, that's the difference between a non-standard basis with a standard basis. Now, here, take a look at this vector x, which is 1, 2, -1. And question says, hey, find the coordinate matrix of this vector in the space relative to non-standard basis B prime, which is given to you as 1, 0, 1, 0, -1 and 2, 2, 3, and -5. Here we go. What are we going to do? As usual, we are looking for linear combination. C1, C2, C3, C4, Cn. Here we're going to stop at C3 because we are in the space, and we're going to list them all. So we have a lot of algebra to work with. X is 1, 2, -1, C1 times 1, 0, 1, plus C2 times 0, -1 and 2, plus C3 times 2, 3, and -5. Now we are applying our skills in algebra to solve this problem. C1 plus 0 C2 plus 2 C3 is equal to 1. We're just basically distributing these into each vectors, combining the first components, combining the second components, and setting these two vectors, left-hand side and right-hand side, equal to each other. For forming this system of linear equations in C1, C2, and C3. Basically, you can form the matrix 1, 0, 2, C1 equals to 1, 0, -1, 3, C2 equals to 2, and 1, 2, -5, C3 equals to -1. These are the coefficient matrix. Now, you can basically solve this. C1 plus 0, C2 plus 2C3 is equal to 1. You can simplify this matrix. How? You can form the augmented matrix and apply elementary row operations. After doing that, the solution is going to be 5, -8, and -2. So x is equal to 5 times 1, 0, 1, plus -8 times 0, -1, and 2, plus -2 times 2, 3, -5. So if I ask you to write down the coordinate matrix of x relative to B prime, it is going to be 5, -8, and -2. They have a nice trick to solve this problem using the inverse of a matrix. We're going to form something that we call the transition matrix. So in previous example, we had the coefficient matrix. We're going to call it P. And these are C values that you're looking for, or the coordinate matrix of x relative to B prime. And on the right-hand side, you have the coordinate matrix for vector v relative to base B. This matrix P is called the transition matrix. So if you simply find the inverse of P and multiply the matrix on the right-hand side by inverse of P, it creates those C values that you are looking for. So again, if your matrix is invertible, you can easily find the inverse of that matrix. This is called the transition matrix. Find the inverse of the transition matrix and multiply by the entries or elements on the right-hand side. It creates the matrix, which is the coordinate matrix of x relative to base B prime. So instead of doing all of these algebra, on the other side, you could just find the inverse of this matrix and multiply it by 1, 2, and -1. Perfect. You can also generalize the idea. Assume that you have two bases. One of them is v1, v2, vn, and the other one is u1, u2, un. There are two ordered bases for n space. If x is a vector in the n space, and you have the coordinate matrix of x relative to b and coordinate matrix of x relative to b prime, then you can easily form the transition matrix P from B prime to B such that the coordinate matrix of X relative to B is equal to P times the coordinate matrix of X relative to B prime. So if you multiply both sides by inverse of P, you can easily find the other one. So coordinate matrix of X relative to B prime is the transition matrix from B to B prime times the coordinate matrix of X relative to B. Theorem. The inverse of a transition matrix, if P is the transition matrix from a basis B prime to basis B in n space, then P is invertible. And the transition matrix from B to B prime is the inverse of P. The sketch of the proof is going to be very easy for you. So I'll leave it to you to prove this, the inverse of a transition matrix. Now, let us move on to a lemma. Suppose B and B prime are two bases for vector space V. If V1 can be written as linear combination of vectors in B prime, V2 the same as linear combination of vectors in B prime. And finally, you can take the last vector in basis B and write it as a linear combination of vectors in B prime. Then the transition matrix from B to B prime can be written as Q, which is C sub 1 and 1, C sub 1 and 2, C sub 1 and n, C sub 2 and 1, C sub 2 and 2. You're basically just listing the scalars. Here, take a look, guys. Here you have C sub 1 and 1, C sub 1 and 2, C sub 1 and n, all right? So you are taking the scalars of U1s and you are forming the very first row of your matrix. Then you're taking the scalars of U2 and forming the second row of the matrix, and so on. So that's how you can easily construct the transition matrix from B to B prime. So again, from B to B prime, you're going to take the entries, vectors of B and write them as scalar linear combination, scalar multiplication, and then linear combination of vectors in B prime. And then you're going to take all the coefficients that you found for U1 and form the very first row. You're going to take all the coefficients that you found for U2 and form the second row. And continue this process. This guy is going to be your transition matrix from B to B prime. And finally, the theorem, transition matrix from B to B prime. Let B and B prime be two bases for n space. Then the transition matrix, inverse of P from B to B prime can be found by using just Gauss-Jordan elimination. You just list the B prime, then B, these vectors, and then apply elementary row operation, convert the very first matrix into identity matrix. The second matrix is going to be the inverse of P. Here we go, finding a transition matrix. Suppose I give you two bases for the space, and I ask you to find the transition matrix. So first use the vectors in two bases to form the matrix B and B prime. So you're taking the very first vector, the second vector, and the third vector to form the matrix for basis B. And then you're going to take the entries or vectors for B prime and form the second matrix. So 1, 0, 1, 0, negative 1, 2, 2, 3, and negative 5. Guys, just be careful about the order that you're writing these down. So 1, 0, 1 is your first column. 0, 1, 0 is your second column. 0, 0, 1 is your third column. The same here, 1, 0, 1 is going to be your first column. 0, negative 1, and 2 is your second column. And then 2, 3, and negative 5 is your third column here. Now, form the matrix B prime and B, and then apply elementary row operations that you learned before. So here you have B prime and B. So B prime comes first, then B, and then applying elementary row operations. Here you have pivot 1, this is 0, but this guy needs to be 0. So multiply the first row by negative 1 and add it to the second row multiplied by negative 1. And as you know, this matrix converts into identity matrix. And here you have the inverse of the transition matrix that you were looking for, all right? So again, B prime and B. Remember that you are finding the transition matrix from B to B prime. Take a look at the order. Write down B prime first, then B. Then apply elementary row operations to convert the very first matrix into identity matrix. The inverse of the transition matrix becomes negative 1, 4, 2, 3, negative 7, and negative 3, 1, negative 2, and negative 1. Multiply the inverse of P by the coordinate matrix X, 1, 2, negative 1. And then you can just see the result that you were looking for. Let's take a look at another example. Given the coordinate matrix of X relative to a non-standard basis B for an space, then the coordinate matrix of X relative to standard basis is what? So here you have this basis. As you can see, it is not a standard basis. You have 2, negative 1, 0, and 1, and this is basically the coordinate matrix of X relative to B. You can write X as 4 times negative 2, 2 times negative 1, plus 1 times 0 and 1, which is 8 and negative 3. So you can basically find this vector using C1 and C2. Remember that this guy is your C1 and this guy is your C2. That helps to write the linear combination. So basically we can say that, hey, that guy was 8 and negative 3. Well, 8 and negative 3 with respect to standard basis is 8 times 1 and 0 plus negative 3 times 0 and 1. So you can write down the coordinate matrix of this vector relative to standard basis as 8 and negative 3. So 8 is the new C1 and negative 3 is the new C2. Again, you can easily find the transition matrix as well and do the computations as we saw before. Next one, find the transition matrix from B to B prime. B is the standard basis, 1, 0, 0, and 1, and B prime is 2 and 4, 1 and 3. Okay, let us begin. First, we're gonna list B prime, then we're gonna list B. Again, 2 and 4 is your first column, everybody. 1 and 3 is your second column. 1 and 0 is the third column. 0 and 1 is the fourth column. So you're gonna write these vectors in column 4. Now, if you apply elementary row operations, this is 2, which needs to be 1. You can multiply the first row by a half, or at this point, you could just say, I'm going to multiply this guy by negative 2 and add it to the second row for simplicity. But again, after doing the elementary row operations, the very first matrix becomes the identity matrix, and the inverse of P is 3/2, -1/2, -2, and 1. So the transition matrix from B to B prime is 3/2, -1/2, -2, and 1. If I ask you to find a transition matrix from B prime to B, you can find the inverse of this matrix, or you can list B and then B prime, and basically this guy is already identity matrix. So this one, this 2 by 2 matrix is the transition matrix from B prime to B. So as long as one of them is identity matrix, the rest of the job is very easy. So as long as you have a standard basis, one of them, one way to the other one is easy, but the other one requires a little bit of calculation, doing a little bit of algebra, elementary row operations, and forming a joining matrix and converting the very first matrix into identity matrix. Okay.